Welcome you to this video lecture. Today we will discuss steady state error for disturbances. Before this, we discussed the steady state error for input. Now, normally, whenever we have our system, so we do have disturbances that come for a very short time and then disappear. So, and when we introduce feedback control system, so main idea is to actually reject the disturbances. Now let's see this block diagram where you have an input or a phase, you have a controller that you need to design, then you have disturbance input to the system, and this is your plant, and this is a unit feedback here. Now if I write the output, so output can be written as because it depends upon the input and also depends upon the disturbances. So if I try to write the output equation C of S in frequency domain, so it depends upon G1, G2 times the error input plus it also depends upon this input, that is DS times G2. So this is your output equation, but as we know that CS actually equals to output actually is equal to RS minus E. Okay, so if I substitute this equation that form and do a little mathematical manipulation, so the main idea is to write the output in terms of error with respect to input and with respect to disturbances. So we get this thing. So the basic idea here is you can do that, just push this to the output and push all things back into the feedback loop. So you will get this transfer functions, and from here you can write the error output in terms of input, RFS and disturbances. Now this is actually a transfer function 1 divided by 1 plus G1 G2 that relate with error and input. Similarly, we have minus G2 divided that relates error and disturbances. Now to find the steady state, so we have to apply the final value theorem, if you remember. So for final value theorem, one of the conditions is that your system must be stable. Okay. So after fulfilling the condition, if I apply the final value theorem, I get the steady state error that I represented by E infinity, because steady state is the output when we have transient server and system is settled down. So that's why we apply the final value theorem so that we get the final value. So we normally represent it as E infinity, that is limit when s tend to 0 s E of s. So just this is E of s multiplied by s and apply the limit. So we get this thing, and we can represent this by ER of theta plus ED of infinity. So the main idea here is that the steady state error depends upon the error due to input minus error due to disturbances. Okay, so if I represent this error by ED and this error by ER, so this is summation of both errors. Now where we know that if this is with the input and this error is with the disturbances. Okay, now the first term, that is with respect input, is a steady state error due to input, which we have already obtained in previous. We discussed what type of input and then system types and then static constants. Okay, now we are interested in the second one, that is due to the disturbances. So first thing, we assume that some assumption about this disturbances and the controller and the plot. First we assume a step disturbances. So We just giving a step disturbance to the system, and that step is represented by 1 by s. So if we substitute here 1 by s will cancel out. So we left with this formula that give us the steady state error component due to step disturbance. Okay. So, so this is the way we can represent or look at the steady state error due to step disturbances. Now let's do an example here. So this is our G1, this is G2, and this is the system. So we have to find the steady state error component due to step disturbances. So first thing is to make this as an input and this as output. So we can redraw a block diagram like this. So we have input. Okay. We have this G1 coming as the output, and this is the minus R. Okay. Now uh, we we can easily solve this block diagram, okay, or we use a formula that we develop. So we just plug in the values and we get 1 over 1000. So this result shows that the steady state error produced by step disturbance is inversely proportional to the DC gain of G1. Okay. So the DC gain of G2 is infinite in this example. Now there's another example that you can do by yourself, and it is evaluate the steady state error component due to step for the system failure in 7.14. So we can you will solve yourself and you get this result. Okay. Now this what we have for disturbances. Now normally when we look at the steady state error and we discuss all the techniques developed till now is for unity feedback system. So if you remember, so this is not always the case because normally this HFS represents your sensors dynamics. So it is not always the case that you have unity dynamics. So you can have different dynamics. You can have a system with non-unity feedback. So how you can solve those type of problems and use the formula that we already developed. So for that case, we just consider some systems here. So first one here is where we have a feed forward term, then G2, then a feedback in GS, and the second one is that we have G of S, then H of S, and the third one we have G of S, H of S, then minus, then there's a loop. So the main idea is that if we want to represent this non-unity feedback, we can represent this into this form. Look here, so how we do that here. What we did here is that we have this loop as it is, but we introduce a minus sign here. Okay, so with that minus sign we introduce another plus here. We know that plus minus becomes 0. So if there's only single line going to feedback, it represents as gain of 1. So here I put minus 1, here is 1. I know that 1 minus 1 is equal to 0. So I introduce these two extra loops, feedback loops here. Okay, so first of all we have to solve this one. Okay, so when we do that we can easily we know that these two are in parallel, the h and minus 1, so these becomes h of s minus 1. After that we can use the feedback to solve this loop. Okay, when we do that it becomes g divided by 1 plus g of s h of s minus g. Now then it is again become unity feedback. So we can apply all the formula that we developed in previous section here. Okay. So the main idea is here to make it a unity feedback system. non-unity we have to convert into a unity feedback. How we do that? Simply, if this is not a unity feedback, what you do, you introduce two loops, one with gain of -1, other is with 1, okay, with minus sign here. Then after that, you know that these two are in parallel, so you can write it h of s minus 1. You have to add the gains. When there are two blocks in parallel, you just add them. So when I do that, it becomes h of s minus with minus sign. Look here, with minus sign, h of s minus 1. After that, I have to take the feedback. So when I do that, I come up with a single block. Now it becomes a unity feedback. So this is the way we can convert a non-unity feedback into a unity feedback. Now example here is this one. So here we have to find the system type and appropriate error constant and the steady state error for unity step input. So step input and just find. So what is mainly what I have to do? I have to convert this into a unity. So how I can do that? I just know that this is G, this is H of S. So I have to calculate this one, because when I do that, okay, in previous section I developed this as the unity with H of S. Okay. It becomes G divided by 1 plus G H minus G of S. So I calculate this block. I call it GE. Okay, equivalent. So when I do that, I come up with this thing. After that, so this is our G. Now, because we have to go for what you say step input, so we can easily find the solution. Before finding solution, let's look at this GE. So there's no pole at the origin, so this means that this is type 0 system. Okay, so first thing after I calculate, we find out that this is a type 0 system because there are no pure integral in the equation. So the next thing is we have to, because we are going for a step input, so we have to find the kp. So kp, if you remember, is limit when s tend to 0 gfe. When we plug in as 0, so this becomes 0, this becomes 0, this becomes 0, this becomes 0. So we have 500 divided by minus 400, so it becomes minus 5 by 4. Now we know that for steady state error we have to find out 1 over 1 plus kp, so it becomes minus 4. So the negative value for steady state error implies that the output step is larger than the input step. Okay. Now to continue further, system with non-unity, let us look at the general system, this one. Okay. Now we can find out error using the equations for disturbances and the input. So it becomes error due to input and error due to disturbances. So uh, we know that the error is based on input minus output. So when we do that to calculate the transfer function, we have error due to input and due to disturbances. So same case, if we look at the unity for disturbances and we consider for step input disturbance, we can calculate the error. Okay. For zero error, we know that the limit this must be equal to 1 so that it becomes 0 error. Okay. Or in other words, this and this the second term goes to 0, then in that case you have a 0 error. So this means that the two equations, that is this one 7.71 can also satisfy in one if the system is stable. First thing is that system must be stable. Second is that system is type 1. So G2 is a type 0 system, hence H S is a type 0 system with a DCT of unity. So the main idea is that if you have a type 1 system, you can have a zero error. Okay, now just to generalize that, what we did here is that we can convert our non-unity feedback into a unity feedback, and then we can easily solve the problem. Now there's a question that steady state actuating signal for non-unity feedback system. So the main idea is that we have to do this figure 7.16 for ramp input. So you just plug in the values and you get the result. Okay? So this is the skill that you have to do by yourself. Now the next thing is known as the sensitivity. So this topic is actually based on whenever you design a system. So you want to know that how sensitive parameters values are during the design process. So um, the main idea is sensitivity calculation tell us uh, the degree to which changes in the system parameter affect system transfer function and hence performance. So we call it sensitivity. So sensitivity analysis is actually used to understand or get the idea about the robustness of the system with respect to parameter changes. So for example, assume that we have a function f that has equal to k divided by k plus a. If k is 10, a is 100, then f is 0.091. If parameter a triples to 300, then f becomes 0.032. We see that a fractional change in parameter a of 300 means 2 or 200% change leads a change in the function values is 65%. Thus, the f has a reduced sensitivity to change. So, the main idea is the sensitivity analysis tell us that if we have the changes, how much we are getting on the performance of the system. So, from here we define the sensitivity um, is the ratio of the fractional change in the function of the fractional change in the parameter as the fractional change of parameter approaches 0. That is, so the formula is that fractional change in function f, fractional change in parameter p. So we have a p and f is function, and we have to take the limit when this parameter change tends to 0. So the main idea is that it just becomes fractional change means that you have to take the delta f divided by f divided by delta p divided by p. So after do some simplification, this cross multiplication, it becomes p del f divided by f del p. So which reduced to very simple relation, and relation is p divided by f times partial f divided by partial p. So let's see how we can use this formula to understand the parameter variation. So just look at this example that will clear us. So here is the example that we have a parameter a here and this controller. So given the system, calculate the sensitivity of a closed loop transfer function to change in the parameter a. How would you reduce the sensitivity? So the main idea, first we have to calculate the closed loop transfer function, and for those closed loop transfer function, here parameter is a. In this formula we represented parameter by p, f our function. So here function is our transfer function, parameter is a. So first thing is to calculate the closed loop transfer function. So we calculate the closed loop transfer function. Now we apply the formula. So formula says that our f is p here. Now we have to take the partial derivative, or we have to take the derivative of t with respect to a, because parameter is a, and then multiply by a divided by t, which is the transfer function. So what we did here, this is the t, so we wrote a divided by t, so this is t, this is a divided by t, times we have to take the derivative of this function with respect to a. When I do that, it becomes, if you remember, this is a denominator, put a line, and on the denominator to put square, and then on the top just put a constant, and then the derivative of this thing, this multiply by the derivative of this, that becomes 0, then put minus sign, then put this as it is, and derivative of the second term. So when I do that, because there's no a here, so this is a constant, this is a constant, so we have left with s, so it becomes minus ks. So this is the way you calculate the sensitivity. When we solve it, it becomes minus as divided by s square plus as plus k. Okay. Similarly, for the system 7.19, find the sensitivity of steady state error to change in parameter k and parameter a with ramp input. So if I look at 7.19, so the same block diagram. So what we have to do, we have to calculate the steady state error. So steady state error for ramp input, if you remember, it becomes 1 over kV. So when we solve the kV, how we solve it for kV? If you remember, we have to take the limit s times g of s times to 0. When we do that, it becomes a by k. Now the sensitivity error to change in parameter is, now this is error. If we look at the sensitivity of this error with respect to parameter a, how we do that? We have to multiply a divided by error times derivative of error with respect to a. So a divided by error, so it becomes a divided by k, so a will cancel out, it becomes k, times, now the next thing is we have to take the derivative of this, that becomes 1 over k, so it is simply 1. Look here, a divided by error times the error divided by a, so when it becomes a divided by k, so it becomes a divided by a will cancel out, it becomes k here. Now take the derivative. So when I take the derivative of this term with respect to a, it becomes 1 over k. When I put in the answer, it becomes 1. So the sensitivity error to change in parameter k is, now let's assume the sensitivity with respect to k, it becomes minus 1. So thus the change in the either parameter a or parameter k are directly reflected in error, and there is no reduction or increase in sensitivity. The negative sign that come up here, what this means? This indicates that decrease in error for an increase in k. Both of these results would have been obtained directly from equation 7.8. Okay, so the main idea is, if you have a negative value of sensitivity, so this means that if you increase that parameter, that will result in decrease there. Okay, if we are calculating for it. Now this I will left for you, you have to do yourself. Just pause the video and solve this example. After this also do this skill assessment exercise, so that you understand what mean by sensitivity. Now the last topic of this chapter is steady state error for system and state space. So actually the main idea here is to apply the final value theorem in state space. If you remember, we have time domain representation here. So what we have to do, we have to convert into, what do you say, frequency domain, and we have to follow the same calculations. So when we do that, uh, we have this formulation for error. Okay, so this is the final value, and we can use this to solve our problem. So for example, this A, B, C. So first thing is to calculate the transfer function. If you remember, we did it. That was C into Si minus A whole inverse times B. So this will give you the transfer function. And then plug in this formula and apply the final value theorem. You usually find the steady state error. So I'm not going in much detail how to do that. So this is enough that you know how to solve for state space using the steady state error. So we will stop here, and actually after this there's an example of design that we are not going to do right now. So this is the end of your chapter number 7, where you have steady state error. So you just go through it. We have 3 to 4 videos on this one, so just go through it and you will get the idea. Also solve examples so that you understand what this means, and especially if I go through it today, we discussed that the main thing is uh, error with respect to disturbances that we calculate based on make input as a D of S and output as an error. You can easily calculate. After that, we discuss a topic based on non-unity feedback transfer function. In that case, we say that we have to convert it. How we convert it? We just put 2 extra loops in it. One with -1, other is with 1. So the main idea is we introduce these 2 loops, and when we do that, so these becomes what you say parallel, so we can add them. So the basic idea is we have to introduce this unity feedback. So for that case, we have to put this with to cancel out the fact we have to introduce -1. So when we add this and then solve the closed loop here, so it becomes this new equivalent open loop transfer function. So from here we can easily use the formula that we develop for steady state error calculations. After that, we discuss sensitivity. What is sensitivity? So sensitivity tells you how what happened if there's a parameter variation, what it affect on the performance. So basically sensitivity analysis we normally use for robustness of the design. So um, how we calculate it is very simple, that what we have to take the limit when del p is 10 to 0, p del f divided by f del p. So if we apply the del p limit to del f del p, it becomes a partial derivative actually del f divided by delta p times p divided by f. So this is the formula that can use to solve the sensitivity problem. So after that, lastly we discussed how to solve for steady state representation. So main idea is that you have to convert into transfer function, then you can easily calculate the steady state error. So here we will stop and we actually complete this whole steady state error analysis and how we can solve this. Now in coming video we will start another technique that can be used for analysis, also for design purpose, and that is the root locus. So that we will start in next video. Thank you.